distinguish between a theoretical yield, an actual yield, and a percentage yield, and then do some math associated with percentage yield. Now, percentage yield is simply a measure of reaction efficiency. It's just like a batting average or a 3-point percentage, which the Blazers are awful right now. I was so depressing last night. I don't know about you guys. It's game over. Golden State in 4, unfortunately. But we calculate it just like we would any other percentage or batting average or free throw percentage or 3-point percentage. It's a very easy calculation. Our equation that we use is percent yield is equal to our actual yield divided by our theoretical yield multiplied by 100 to get us to a percentage. Yield, what we get out, or product. Okay. Not yield. Yield. We haven't done this yet. We did percent error, which is almost the same thing. Now, a couple notes here. Actual yields. Actual yields mean data that you collect in the lab. So you run the reaction, you take the mass, and you're like, ha, this is what I actually got. So when we did our moles of iron and copper lab, our actual yield of copper was the mass left over in the beaker at the end. And a theoretical yield is something that we determine using stoichiometry, using the calculations that we've learned how to do. So that's always done on paper. Now, all of these problems look similar. And there's really only 2 things that you can be asked to do. One, you can be asked to determine the percentage yield. And in that case, they have to give you this value because you can't figure that out. And you figure out this value, and then you just multiply by 100. Pretty easy, right? The other type of question they can ask you is predict how much we would get if we actually did the reaction. In that case, they've got to give you a percentage yield. We figure out the theoretical, and then we figure out the actual yield. And so there's not a whole lot of variance in these problems. They're very straightforward, and there's no trickeration there.
So what's the theoretical yield again?
We always do stoichiometry to figure that out. It's like a mass calculation.
Okay.
Yep. We're always figuring that one out. All right, so let's look at a couple of practice problems here. So usually what we see is the questions kind of come in pairs, or they're in 2 pieces, and we always have to do the theoretical calculation first before we can do the percent yield part. So with this question, it asks us, what is the theoretical yield of calcium oxide if 24.8 grams of calcium carbonate is heated? And we know how to do this. This is going back to like what we first learned how to do in mass calculation. So we will start with what we're given, 24.8 grams calcium carbonate, and we're going to work forward to our mass of calcium oxide. So 1 mole of calcium carbonate has a mass of 100.08 grams. Our mole ratio, according to our balanced chemical equation, is 1 to 1. And then our molar mass of calcium oxide is 56.08 grams. Once we get done crunching the numbers, we find that we should generate 13.9 grams. Of calcium oxide. That's what we should end up with. That's what we call our theoretical yield. So once we found our theoretical yield, then we can move on to the second part of the question, which asks, what is the percentage yield? And here's where we need to remember our relationship that we just saw a minute or two ago. Our percentage yield is equal to actual divided by theoretical multiplied by 100. So in this case, they provide us with the actual yield because they're asking to calculate the percentage yield. So what is the percent yield of 13.1 grams calcium oxide is actually produced? So we're going to take 13.1 grams calcium oxide divided by our theoretical yield, which was 13.9. We did the stoichiometry to figure that out. Multiplied by 100, and we should end up with, I think it's like 74 or something. Oh, shoot, that was the next one. 94.2%. So not a whole lot of new stuff here. Just, we're doing the same stoichiometry, now we're just taking it one step further. Do you think you need to see another problem like this, or do you want to see one where we predict the actual? Yes, before we move on.
What would the, like, 6% mean? What does that mean for your accuracy of the problem?
That's a great question. Can you ever get over 100% yield? Well, you can find that you have over 100% yield. Let's see, it was a second period when we were doing the calculations for our lab. Somebody determined that they had 181% yield. Okay. Now that indicates lab error, right? So if we do the calculation, we end up with over 100% yield. We know we messed up somewhere, and it's either there's an error in our math, which probably isn't likely because it's fairly straightforward math. More than likely, there's an error in technique. Okay. The other thing that this tells us is that not all reactions go to completion or are 100% efficient. So up until this point, we've kind of had this mindset of, hey, if I mix these things together, they'll react. And then we learned in chapter 8 that not everything we mix together reacts. And now we're learning that not everything we mix together that does react goes all the way to product. Sometimes it stops part way. Now this gets really interesting later on. I remember in college I took organic chemistry, and our professor's name was Paul. He was a pretty cool dude. He didn't like Dr. Chamberlain or anything like that. He was a first name guy. But he terrorized us because in lab we would do these really complicated synthesis reactions where we'd be making a product. Like we'd make aspirin from just a bunch of different materials. And at the end, we would have to weigh our product to figure out how much we got. And then we'd go back and do the math to figure out what our theoretical yield was, and we'd be evaluated on our percent yield. Now, he would not tell us what our percent yield should be, because not all reactions go to completion, not all reactions are 100% efficient. And I remember distinctly, like, hey, we had a 3-hour lab period, worked all 3 hours in lab, go back home, spend time working on my lab report. I get to the end of it, and I'm like, oh my, I have 12% efficiency. I have 12% yield on this. I'm going to fail this lab. Well, no, because really, like 14% yield was amazing for that particular set of reactions. And so we kind of see with this percentage yield, like not all reactions go to completion, not all of them are 100% efficient. And it's just a measure of efficiency for us.
So that's a really efficient reaction then?
Yep. Almost all of your reactants are converted into products at that point. So this indicates either the reaction is super efficient and you had good technique. Okay. And we'll see when we do our calculations for our lab. So the lab that we did with iron and copper should have been 100% efficient, or almost 100% efficient. And we'll need to evaluate our lab technique and see how we did. Okay. Let's look at one more practice problem before we do go to the lab. And in this instance, we're going to determine our actual yield. This is problem number 7 on one of the homework assignments. So I flip to that one. It's number 7 on the first one. So it's number 7 on the first sheet. So looking at this problem, it says aluminum reacts with excess copper 2 sulfate according to the reaction given below. If 1.85 grams of aluminum reacts, and the percentage yield of copper is 56.6%, what mass of copper is produced? Okay, so in this instance, it helps us to keep in mind our equation looks like this. We can always determine our theoretical amount. We're given this value right here by the question, so that means we need to find that one. So if we do a little algebra to isolate that variable, we end up with theoretical times my percent yield is going to equal my actual yield. So that's how I'm going to end up determining this. Hey, no cast. Congrats.
Alright, boy.
Yo, skinny Chris. You been there before?
Yeah.
Alright, so let's start with our given reactant. We have 1.85 grams of aluminum. We're going to go all the way through and figure out our mass of copper that we should be producing. So first thing we got to do is convert from grams to moles. Then we're going to use our mole ratio. That's not the balanced chemical equation, by the way. It should be 2 to 3. Very good. Who was that? Was that Connor? Nice. From the bleacher seats. And then 1 mole of copper is 63.55 grams. Okay. We run through the math. We should get out 6.54 grams of copper at the end of this one. Let me double check. Yep, 6.54. Okay, so because we did stoichiometry and we know that this is my theoretical yield, so this is my T. I'm going to go back up here and I'm going to take my theoretical yield, 6.54 grams of copper, and now I need to multiply it by my percentage. And it says my percent yield is 56.6%. It's very important to remember here, if you're asked to find the actual yield, you need to use the decimal version of the percent yield. Why would we need to do that?
Because you're like a percentage is out of 100, which is kind of out of 1 if it's a decimal.
What happens if we don't put it in a decimal form?
It's
It's
too
gonna be a
big.
huge number.
It's going to be a huge number. That would mean our actual yield would be over or larger than our theoretical yield, which isn't possible if we've done our work correctly. Okay, so we multiply this out, and we end up with 3.70 grams of copper being produced. And so again, this is the power of stoichiometry, is that we are able to make real world predictions about what we should get. This is supply chain management. If I'm a pharmacist, if I'm working in a pharmaceutical production facility, I know I'm going to get this much product out. I know what I need to purchase in terms of shipping, containers to move my product out. I know what I need to purchase in terms of reactants to get this amount of product. We now can figure out how much excess we're going to have left over that either needs to be recycled or disposed of. So there's a lot of practical implications to what we're learning right now. Yes?
Do you guys do this Navy camp stuff too?
Yeah, but we blitz through it and then it just stays consistent throughout the year with what we do. So, any questions on this before we get our labs up? I want to help you guys with your lab real quick. Yes.
Well, it's kind of, but like, number 8, isn't it saying that, isn't it asking the exact same question?
Yeah, it got doubled up on there. Yeah.
So dumb.
Don't do number 8, so we should just say that's 7 there. Okay. All right, let's take out our lab books, and I want to walk through the lab real quick. That was it.
I'm gonna get home tonight and I'm gonna try and do it. I'm doing it really awesome.
No thanks, Jordan. That was it.
Somewhat.
Oh, yeah,
That
I
was-
was out.
You didn't, yeah.
All right. So everybody's got their lab in front of them. We should have already answered the first 4 questions in the post lab. And so now we just need to pick up with number 5. Number 5 is asking us to determine the theoretical yield of copper based on the amount of iron that was consumed in the reaction. And so if you look at your data table, and I'll scroll up here. If we look at our data table, we need to know the mass of the iron used in the reaction, or the mass of the iron consumed. So it's this space right there, the mass of the iron used in the reaction. That's going to be our starting point. Who wants some help with their math? Paige, hand up first. Good work.
I don't know.
Okay, so what was your mass of iron consumed?
0.23.
0.23. So this is the start of question number 5. So we need to figure out theoretically how much copper Paige, who is your partner? Paige and Ashley should have got at the end of the reaction. So we're going to convert from grams of iron all the way to grams of copper. And we know how to do this. So we're going to use our molar mass. We remember that it was a 1-to-1 ratio. And then we use our molar mass of copper again at the end. So you gotta do the math there. Get those thumbs moving.
It's 0.26.
0.26 grams of copper. Okay. So that would be our theoretical yield, as it states in the question. Okay, so then number 6 says, using the theoretical yield determined in question 5, and the actual amount of copper produced, determine the percent yield of the reaction. So we're going to use percent yield equals A divided by T times 100. And we know that our theoretical yield was 0.26 grams of copper. What's your actual yield? So going back to our data table. How much copper was left over at the very end of that night? I gotta get there.
Like
So.
produced, mass copper produced.
Yes, mass copper produced.
0.37.
0.37.
0.7.
0.37.
I got 0.21.
Yeah, I got 0.2.
Well, you guys is gonna be different based upon the amount of iron consumed. It's all.
Well, we use the same basically.
Okay. So Paige, you see a problem? What's the problem?
People got different numbers.
No, I mean, what's the problem here?
Bigger than the other one.
It's bigger, so what is your theoretical yield, or your percent yield gonna be?
Bigger, it's over 100.
Over 100. So either you have figured out how to defy the physical laws of the universe and create something from nothing, or there might have been an error with the experiment.
I mean, it's paid.
It is Paige, it's possible that you figured out how to violate the laws of the universe. If you can do it on a consistent basis, you can make a lot of money doing this. But I'm going to go out on a limb and say it's not that. So really quickly, thinking back to the experiment, what is the most probable source of error right here? water in the beaker. That's the obvious one. When your mass is larger, when your actual mass is larger than your theoretical mass. The very first and easiest thing to do is say, hey, you still have water in your beaker. Do you remember if you still have water in your beaker?
I mean, maybe a little bit.
Maybe a little bit, okay. So yeah, that's probably where you went wrong. It wasn't completely dry. So we would calculate our percent yield, which is, what's the percent yield for this one? Two.
That's 140.
142%.
Oh, I can't.
Yeah. Okay. Let's see, we're on Wednesday, right? Okay, so here's what I would recommend. I would recommend finishing problem 7 and 8. 7 is super quick and easy. 8 should not take you that long either. And then your lab will be done. We're going to evaluate these at the beginning of the period tomorrow. Once you've got those two things done, then I would go to the